All right, so minute, okay, it is recording. Okay, so hi and welcome back to this new video of our channel. So, in the last video, in the last two videos, you have learned about Python. So, I just taught the basic, very basic concepts, but like you should definitely read some documentation and practice before coming into this video, because in this video we are going to develop a neural network from scratch, right? So we are going to learn a lot of concepts today. So yeah, there is lot of things to know today. So first, uh, you know first learn about derivatives. Sorry. So first we'll learn about derivatives, and we are not going to go into the depth of calculus, and we are not going to go into the depth of calculus and how to calculate derivatives and what is the meaning of derivatives. But you know like to be like overall, the concept is slope. So calculating derivative is calculating derivative means calculating slope. What is the slope of function means? The slope of a function essentially is, it just defines how the output changes, right? So how the output of the function changes. So the slope of function, wait a minute. Okay, so yeah, as I've told you, derivative, calculating a derivative means calculating the slope of function, right? So the slope of the function defines how the outputs will change if there is change in the if there is a change in the input. For example, to understand this, let's say there is a function f of x. Sorry, right? So let's say there a function. Okay, so there is a function f of x, which gives us a value of 10x. Right. So what we are going to do is we are going to see how this output 10x will change if there is a slight change in the input x. So here, as you know, as you might guess, the slope here is 10, because even if we change it in a very slightly manner, it is like the slope, like between two input points there is going to be an increase of 10, right? So you can understand, right? So that is what slope defines. Slope defines, yeah, the change of the output given the change in the input. So that is the basic, probably the basic definition of what is a slope and what is a derivative. Now let's see how we can calculate it, like mathematically, not let's see like how we can calculate it. Okay. Okay, so let's say you have a function like x square. So this is the function. So there is a rule in calculus called power rule, in which this is the formula. So let's say if you have a function with x to the power of n, let's say a function f of x is equal to x to the power of n, then the derivative of x, f of x. So this symbol here represents the derivative. Right? So derivative of f of x is equal to, right, n into x to the power of n minus 1. So this is a rule. So what is going to happen is, if I have a function called x of x to the power of n, then the derivative of f of x is equal to n into x to the power of n minus 1. So here the derivative will be what? 2x. Right? So the derivative of f of x function here is 2x, right? So this is called a power rule. This is called the power rule, and we are going to use this rule to calculate the derivative of um, loss function, the loss function that have defined in the past few videos, the mean squared error loss function. So we are going to use this law to calculate the derivative of the final derivative of the loss function, right, with respect to the output. So this is called the power rule. And then the next rule, it is not a rule. Let's say you have a function called let's say a function, let's say something like f of x. Sorry, f of x is equal to wx, let's say you have a function f of x equal wx, then the derivative of f of x, right? So derivative of f of x equal w equals w, because the change will be w, right? So the rise over run is equal to w. Okay, so here what we are going to do is we are just going to get the coefficient of x. All right. So this is like this is the basic thing how you can calculate derivatives, right? So this is the basic concepts inside of this field. So how you can actually calculate derivatives, right? So I'll just move this up now. Let's come to the case of neural networks, right? So I'll just make some points. First I'll just make some you know revision, like what I have learned in the last few videos. Like I didn't explain that clearly to you, but there are some concepts, right? So first there is a forward propagation, right? So you just have, like, for every row, right? For every row in the data set, you are going to calculate this operation. Like in the given data set, you are going to have inputs and the outputs. So you are going to give the inputs to the neural network. The neural network is going to predict an output, and you are going to compare this output, the neural network's output, with the actual output. And then based on that, you are going to update these whole weights. So that is the concept that we have learned. Let's see. So, like, the input going through the neural network. So what essentially is happening is this input is going through the neural network, and each neuron will update this input such that it will be converted into output. So, right. So this process of the input going through the neural network is called forward propagation, right? So the output is the input is going through the neural network, and hopefully it is getting converted into a newer value. So this propagation of inputs in a neural network is called propagation, forward propagation. And then what is going to happen is we are going to as I told you, we are going to update the internal parameters of these neurons, which give us the output, right? We are going to update this, and then to update that, we are going to use chain rule in calculus. And and the function is of the chain rule is that we are going to, like, if you want to first you can calculate the derivative of this neuron's output with respect to the loss, because this is the last neuron. And then we are going to calculate for this layer, and then this layer, and then this layer. So it is called backward propagation, right? So this is input layer. So we don't these are not neurons. These two circles are does not represent neurons. So all these all these three layers, all the neurons of the three layers are actual neurons, and this is just a diagrammatic representation of this input values. Okay, so yeah, in order to change the values, we are going to um, get into another loop called backward propagation, where we are going to first update these parameters, and then some type of value, and then a value, like, the derivative of this neuron's output with respect to the loss function will be calculated by this neuron, right? So the derivative of this neuron's output with respect to the loss function will be calculated by this neuron. It will be passed up to all the neurons, like the respectively. Okay, so that is what is going to happen. We are going to propagate from the back. So the derivatives of each neuron's output with respect to the loss function will be given to each neuron. And then what has going to happen is each neuron will update its own weights, right? So that is the basic, as that is the only basic requirement of back propagation. We are going to update its internal weights. Right? So this is, I hope you can understand it. When we are going to build this in Python, we are going to understand it a lot more. So let's see how these values get calculated. I'm just going to move this up. Okay, let's see how these values are going to get calculated. All right, let's see. Yeah. So in order to update the weights, right? So we are going to be needing to calculate some values, right? So the first value, of course, is the derivative of the error, or the loss function with respect to the weight. let's say w, here let's say w11, right? So before that, for this case, for this purpose, for the purpose of this video, we are going to calculate the, let's say, derivatives of this layer. So we are going to update, let's going to understand what's going on in every layer of this neural network. First we are going to understand the updation. We are going to, yeah, we are going to understand the updation in this neural network in this layer, and then we'll be going to generalize the function. So first we are going to calculate, this is, this is 2, right? So for to first we should, let's say first we'll calculate the derivative of this weight, and then we are going to generalize it. Okay, so let's see how we can calculate the weight of this, yeah, the derivative of this weight with respect to the error function. So as the chain rule says, this is equal to dy2 by w21, right? Wait a minute, sorry. Right, so the derivative of error by the output value y2 multiplied by the derivative of y2 by the output, by the weight value w21. So hope you can understand what is going on here. So we are going to in order to calculate the derivative of error with respect to the uh, weight number 21. First, what we are going to do is, according to the chain rule of calculus, what we are going to do is, first we are going to, like we will be, like for this layer. So for every neuron, we are going to get this value from the previous layer. For example, for this layer, for each neuron, um, an output will be sent back, right? So in the back propagation, this neuron will calculate a value, the and the value is the derivative of each neuron's output with respect to the loss function, right? So we are going to, like, this value is the input to this layer, right? Will already have this value, whatever that is, and what we are going to do is, and we are going to multiply that by the derivative of y2 by w21. And since w21 only appears in y2, we are only going to include this value, right? So we are not going to include y3 and y1, even though they affect the loss function, right? So what is how much is the value? We can just calculate it. D derivative e derivative of error by y2, and then what multiplied by what is w21. What is the derivative of w21 with respect to y2? It is x1, right? Because w21 is only is, like, x1 is the coefficient of w21, so we are just going to say into x1, right? So this is true for any neuron. So if you just take let's say, for example, if you take this weight, then the derivative will be derivative of error by y3 multiplied by x1. So that will be the derivative. Like, we can just generalize this operation for all the weights here, um, right? So now let's calculate the derivative for bias. So now we'll calculate de by db, right? So here, now what are we going to calculate now is, we are going to calculate the derivative of b1 with respect to the error function, or, right, how this b1 affects the error function. Well, in order to calculate that is pretty easy, right? We'll get the same function here. I'm just going to, yeah, what we'll get is, we'll get de, let's say we are going to calculate for b2, right? We are going to calculate for b2, let's say, then it is going to be de by dy2 and into 1. Why we are going to put 1 here? Well, because there is no coefficient for b, right? So bias, we just add bias separately. So as we don't have any coefficients, we are just going to multiply that by 1. So it is just going to be derivative of e by derivative of y2, right? So this is pretty straightforward, right? So the input, right? So the input we are going to get from the previous layer in the sense of back propagation. The input we get from the previous layer is going to be the derivative of b2, right? Is going to be the derivative of b2 with respect to the error function, right? Understand? Now what should we calculate? Well, right, so as I've told in just like a few moments, right, so we should calculate the derivative of error function with respect to each of our inputs. So now let's say in this layer we have three inputs, right? So every neuron, each neuron has three inputs, and like every neuron has same inputs, right? This neuron has same inputs, this neuron has same inputs, and this neuron has the same inputs. So what we are going to do is we are going to calculate the derivative of each of these neurons outputs, right? So this neurons output is, so these neurons outputs are the inputs of these neurons. So we are going to calculate the derivatives of this neuron's input with respect to the error function, or we are going to calculate the derivatives of this neuron's output with respect to the error function. Let's do that now. How can we do that? Well, let's see. We have dE by dx. Let's say we are of error with respect to the y1, with respect to y1, and then what is and then we are going to calculate the derivative of y1 with respect to the derivative of x1, right? So the derivative of x1 with respect to y1, and then we are going to add that with the derivative of next. So we are going to add that with the derivative of d of y2 multiplied by d y2 by dx1, and then we are going to do the same for the next neuron also. So how we can write this is mathematically. So how we can write this is all right. So there has been a little problem for the in the system. So let's continue. So we can expand this, right? So we can expand this into derivative of error by y1 multiplied by, so what is going to be the coefficient of x1 in y1? It is going to be w11, right? W11 plus, and we are going to do the same for the rest of this neurons and layers. So you understand the thing, right? So hope you understand what is happening here. Like this is the main derivative, and this is the root of the previous two derivatives. So we are going to calculate that, and mathematically what we can do is we can just if you are aware of linear algebra, and if you are aware of matrix multiplications and all that, right? So if you are aware of matrix multiplication, what you can write it as, you can write it as W transpose, where W is a vector, W is a matrix in which all of W values in the layer. So let me just show you, right? So we are calculating for this layer, right? So we are going to create a matrix called W, and this W is going to hold all the weights into just one matrix. So it is a matrix in which all of these weights are stored, right? So right, hope you understand. So we can just write it as, okay, so very sorry for the problems, right? I think there is a problem with my computer. Okay, so what we are going to do again is we are going to create another matrix which holds all the values of derivative of error with respect to y. So this is also a matrix in which we hold all the values of d to the power, right, derivative of error with respect to y1, y2, y3, and up to y3, right? So we are going to have that. And why are we transposing it? What is meant by transpose is, let's say you have a matrix of uh yes, let's say you have matrix of a times b. So right, a value right, sorry, a number of values and b number of values, what this transverse function is going to do is it is going to convert this matrix into b by a matrix, right? So we are going to use this function because to match up the shapes, and then we are going to multiply that by the matrix of all the values of the derivative of error with respect to all the outputs of the neurons. So that is how we can calculate. Right? So these three are the values. As I told you, these three are the values we need to calculate in each step. Now let's program it. Right. So I think the computer is getting slower. I'll try to record it now, or okay. So I think today that's it for this video. That's it, and in the next video, we'll try to code the neurons. Sorry for the disturbance in the middle, but yeah, hope you can understand this. I'll just try to go on the video maybe two times and just try to understand what is going on, because this is important, right? You can just understand what is happening with the updation of each weight, and you have to understand the back propagation method. So thank you for watching, and yeah, sorry for the disturbance, and see you in the next video where we can program this neural network in Python from scratch.